So have you ever stopped to think about how your phone call even works? I mean, there are thousands, maybe millions of people all trying to use the airwaves at the exact same time. How is that even possible? Well, it all comes down to sharing. And today, we're going to break down one of the fundamental ways we do that. It's called Time Division Multiple Access, or TDMA for short. And trust me, it's basically a perfectly timed dance of data, and it's way cooler than it sounds.
All right, here's the game plan. We'll start with the basics. What exactly is TDMA? Then, we'll see how it actually shares a channel over time. Next up, we'll get into the really tricky part, the synchronization challenge. After that, we'll look at the clever ways they solve that puzzle. And we'll wrap it all up with a look at the big picture, the good and the bad of TDMA.
Okay, first up, what is TDMA? It's all about the principle of taking turns. You know, that name, Time Division Multiple Access, sounds super technical, but it really just tells you the whole story. We're giving multiple people access by dividing up time. Simple as that.
So here's the official definition. TDMA is all about dividing one communication channel into different time slots. This lets a bunch of users share the same frequency, but they do it by taking turns. The best way to think about it? Imagine a super organized, super polite conference call. Instead of everyone talking over each other and creating total chaos, each person is given a very specific, scheduled moment to speak. You get your slot, then I get mine, then the next person gets theirs. It's this simple, turn-based system that makes it all work.
Let's break that down a bit more. The key here is that everyone shares the same channel, the same big chunk of bandwidth. But, and this is the important part, they use it at different times. Each phone, or station, is assigned its very own time slot. So your phone transmits a quick burst of data in its assigned slot, and then it just stops. It goes silent. And that's the cue for the next phone to take its turn. It's this on-off pattern that is the absolute heart of how TDMA functions.
Okay, so we're talking about time slots and taking turns, but what does that actually look like? Let's visualize how TDMA organizes this whole thing.
All right, check this out. You see that continuous data stream? In the world of TDMA, we don't just send that all at once. First, we chop it up into these bigger chunks called frames. Think of a frame as like a container. Then, inside that container, we divide it up even further into these individual time slots. And you guessed it, each user gets one of those slots. So user 1 gets the first slot on the frame, user 2 gets the second, you get the idea.
And here we can see that whole process in action. Look, you've got frame 1, and then right after it, frame 2. It's a continuous repeating cycle. You see, user 1 transmits, then user 2, user 3, all the way to the last user. And as soon as that last user slot is done, bam! The whole thing starts over again with the next frame. This constant, predictable pattern is happening for both the uplink, that's you talking to the cell tower, and the downlink, which is the tower talking back to you.
So far, so good, right? It all sounds pretty neat and tidy. But there's a huge catch, a really big one. This entire system, this beautiful, organized dance of data, completely falls apart if the timing isn't absolutely perfect. And trying to get perfect timing in the real world? Yeah, that's where things get complicated.
So that leads to the big question, right? If everyone is sharing the exact same channel, just at different times, how on earth do they all stay perfectly in sync? What happens if one person's data spills over into the next person's time slot? How do you stop it all from becoming a giant, jumbled mess?
Well, there are a couple of major roadblocks. First, just getting multiple devices to agree on what time it is down to the microsecond is ridiculously hard. Their internal clocks are just never going to be perfectly aligned. But there's another, even bigger problem: physics. Signals don't travel instantly. We call this propagation delay. If you're close to the cell tower and I'm far away, my signal literally has a longer journey to make. That slight delay can be enough to make my data arrive late and crash right into the next person's time slot.
Okay, so we have a pretty serious timing problem. But don't worry, the folks who designed TDMA were incredibly smart. They saw this coming and built some really clever solutions right into the system to solve this whole sync puzzle. Let's dig into how they pulled it off.
Solution number 1 is so simple, it's brilliant. It's called guard time. All it is a tiny, empty gap, a little slice of silence that they stick between each user's time slot. Think of it like a buffer zone. It's there to make sure that if one person's data runs a little long or the next person starts a little early, they don't crash into each other. This little gap absorbs those tiny timing errors and keeps everything from falling apart.
The next solution is a bit more high-tech. It's called a preamble, or synchronization bits.
Basically, it's a special, unique pattern of ones and zeros that gets tacked on to the very beginning of every single data burst. The receiver is constantly listening for this specific pattern. As soon as it hears that preamble, it's like a signal flare going off. It knows, aha, the data I'm waiting for is starting right now, and it can sync its clock perfectly for that one little burst.
All right, so we've seen the core principle of TDMA and the clever tricks it uses to handle timing. Now it's time to zoom out and look at the whole shebang, the good, the bad, and the ugly of TDMA.
So what's great about TDMA? Well, for one, the scheduling is pretty straightforward. It's a very logical, structured system. It was also a natural fit for digital communication, which is exactly why it became the backbone of massive systems like GSM, the 2G network that really brought mobile phones to everyone. It was a proven, reliable workhorse. But of course, it's not perfect. There are some pretty big disadvantages. The number one problem is spectrum inefficiency. Think about it. What happens if it's your turn? Your time slot is up, but you have no data to send. Well, too bad. That slot stays empty. It's just wasted. That's precious bandwidth that no one gets to use. And remember those essential guard times? They're buffers, which means they're also not carrying data. So all these little gaps add up and can slow the whole network down. Plus, the system can be a little sensitive to jitter or variations in those transmission delays we mentioned.
This little table here really pulls everything together nicely. How do we separate users? With time slots. What's the biggest hurdle? Time synchronization, for sure. How does it transmit? In these discontinuous little bursts. What's the capacity limited by? Simply the number of time slots you can create. And the complexity? It's moderate, because you absolutely have to get that sync right. This is a great little cheat sheet for the whole system.
So, where does that leave us? Let's be honest, pure TDMA is kind of old news, but, and this is the key takeaway, that core idea of taking turns, of slicing up time to share a resource is absolutely everywhere. It's a fundamental concept that's still a building block in our modern 4G and 5G networks. It makes you wonder, doesn't it? How does this simple, almost old-fashioned principle of taking turns continue to shape the incredibly complex communication systems we rely on every single day?